Okay.
I love writing. No, I just like going. And like, you guys say like going fast and back. I just like going through long Yeah, because it's super big, and it's not just go for a couple days. I haven't been to any. I haven't. I've been around.
I'm like shocked.
I'd like to.
Like you can definitely tell.
Okay. There we go.
She was a one of the instructors. She was spreading like
Was she the girl who said something about
It'll take about 2 days to get off. I was thinking I'd like to get a 9 day.
learn about this stuff?
But then I couldn't have 2 days to go off.
All right, so here we are. I think I'm almost ready for this to happen. So we'll start and see what happens. What's going on here is that we are on the 25th of July, and so there's no homework due for today, but we're going to be talking about our next unit here. The way this is going to happen is that these next three things, which are the next two homework sets, are all connected, and then the last two are different. So we're going to be talking about two major topics here in the fourth. My plan and hope is to have your test graded and returned by Monday. It might not happen. Now, for this particular topic, it is really important that you know how to use the computer in order to answer the questions, because you're not going to be able to do this stuff by hand, at least not very easily. It would be crazy to try. So what we're going to try to do then here is we'll go for about 45 minutes right now, and then we'll go take a break, go for another 45 minutes, and then we'll go over to the computer room so that you can try out the things that you'll need to be doing. To my mind, it actually works really well, and it's really easy, but of course, if you haven't seen it before, it might not be. So any experience you have using Excel is probably going to be beneficial to you. And if you don't, well, that's why we're going to go over there. We're going to work on it. Okay. Specifically then, when we look at the notes sections on Blackboard here, we have notes that are listed here from chapter 10. So this is what we're going to be working on. And so this is going to be our main topic for the next couple of times. And so what we need to do is to put this in context, right, of what we've been doing. And I worked on this a little bit earlier, but so after the first 5 times we did this, I would think that you would be a little bit quicker on the uptake. However, I realize it's been a while. So yes, I want to know this. What does this mean? That's almost there, but that's a little bit after what I wanted to say. Okay. What to expect? Danielle, what does that entail?
To determine the unusual and the usual.
The unusual and the usual. What does that mean? Now, excuse me, for any of you that are actually writing this down, You should have had this written down 4 times in your notes already. And that's fine if you want to write it down again. But when you're writing down something 4 or 5 times in your notes, maybe that'll help you to remember. Maybe. But maybe you should have in your notes something where this is really important and we've talked about it 4 different times. And maybe you've got a highlighter or a star or something you would put next to it. Because I'm going to ask this question every day from now to the end of the term. And it's really good for you to know it. You know what else is true? I'm never going to ask this on the test. Because I actually want you to learn this. And I don't want you to ever forget it. And I'm going to ask you every time. And you should know this. What's the purpose of statistics? Data-driven decisions. What does that mean? What to expect? What is that? Usual and unusual. What does that mean?
Less than 5%.
Less than 5%, which would be what thing? The unusual is less than 5%. What's the usual? No. What? Greater than 95%. If something happens more than 95% of the time, that is what I can say will happen. Okay? What if something's in between? What if something's like 30%? What should we say about something that happens 30% of the time? It might happen or it might not. We're not sure. Okay? If it happens less than 5% of the time, we would be surprised if it does happen. If it happens more than 95% of the time, we would be surprised if it didn't happen. So this is how we know. This is what I kind of expect to happen. Something that happens 95% of the time. This is what I don't expect to happen. But if it's 30%, I don't know. It could happen. It might not. Okay? Why do we use these words of probability when we're talking about statistics? What is the reason for doing probability in statistics? What does that give us?
Using a sample to measure something about population.
Nope, that would be the process of statistics. What I want to know is, what is the word that is associated with probability? Valerie? Nope, sorry. It's a character trait. What character trait is associated with probability? Humility. Humility tells us that we don't know what's going to happen a lot of the time. So then we have to say, I don't know what's going to happen a lot of the time. So then we say, if I give somebody a treatment for a medicine, if I say, well, you know what, it's going to increase the chances that you're going to recover from this sickness. But if you don't, okay, then maybe there's some other treatments that we can use. Or if you say something like, if you give orange juice to these senior citizens, it's going to affect them in some way. And then you say, well, I'm not completely sure, but I think it will do this, whatever it is. So you have to have humility because you don't always know what's going to happen. Okay. So what else do we need besides statistics and humility in order to make data-driven decisions? Experience. Because we don't actually know what is important about a situation unless we have experience doing this. Okay. All right. If you have this written down in your notes, I want you to somehow be able to mark this so that you'll be able to refer to it next week on Monday and Wednesday, and the week after that on Monday and Wednesday when I ask these same questions, right? Because I'm always going to be asking these questions, and I want you to be able to answer them, all right? Okay. I want you to know this. Once again, I'm never going to ask you this on an exam because I want you to know it all the time. Not just to study it for an exam. I want you to know it every time you walk into the classroom. Okay. So there is then the process of statistics. Natasha, what did you say the process of statistics was?
We use a sample to measure.
Using the sample to understand the population. And there are two ways we do that. What are those two ways? Confidence interval and hypothesis testing. What is the purpose of the confidence interval? No. I'm sorry?
Show the variations.
Kind of, but not really.
To measure something of a population.
It's to measure something about a population. So if I say I want to understand vitamin levels in apples, I want to understand that. If I use a confidence interval, then I'll be able to measure like vitamin C. I don't even know, vitamin C levels in apples. So if there's vitamin C in apples, I can use a confidence interval to know how much vitamin C is in the apples. Okay. But if I use hypothesis testing, then I'll be able to prove something like Wisconsin apples have more vitamin C than Minnesota, or something like that. So hypothesis testing is specifically looking at some way to prove that something is different, whereas confidence intervals just tell you what the number actually is. And it's up to you to decide what is important about that. Okay. Now, what are the types of measurement that we have done so far? Proportion, mean, and standard deviation. And specifically, we have done these three things with both confidence intervals and hypothesis testing. But we're going to have to think about the type of data that we have. There are different kinds of data when we do this. Specifically, we've been looking at single samples, where I would go out and get a bunch of apples and find their vitamin C levels. It would be in Wisconsin or whatever else. What we did not do, what we skipped, was part B, which was 2 samples. So that we would compare like sodium levels of people in La Crosse versus on Alaska. 2 different groups, and we say, are these groups different from each other? We skipped that part. And now we're going to talk about a third kind of data. This third kind of data is well, I'm not gonna go bigger than that. Okay. I suppose I'm going to try to make this easy. We're going to measure two numbers. From person. Or source of data, whatever it is. So I would ask somebody two questions and I would get two numbers from them. I would say something like, how much did you spend on recreation last month? And how many doctor visits did you have last month? And so I'd be asking them for two different numbers. Or I could say something like, what's the population of this county and how many people got arrested in this county? So it could be those kinds of things. But I'm asking for two numbers. Every time I get a measurement, I'm getting two numbers. And so then what we call this is what I've got listed up on here on the screen, which is ordered pairs. And specifically what that means is X and Y. So that when we have two numbers, we're going to pick one of them to be an X value and the other one to be a Y value. Now, most of the time when we do this, we're going to have something that is known, that would be on the horizontal, and something that's predicted, that would be on the vertical. So if I know something, like I know the person's sodium level, then I'm going to predict their blood pressure or something. Or if I know how much water somebody drinks, then I'm going to predict how many hours of exercise they do. Or the other way around. I could do it either way, okay? It's just a matter of how I choose to do it. It's very important for you to understand that this horizontal scale is X, and this vertical scale is Y. So then we're going to have things that go on the horizontal and things that go on the vertical. So what that's going to mean for us is what's called a scatter diagram. A scatter diagram is where we have a data set, and the data set becomes normally a cloud, a set of points that are scattered onto a graph. Emily Grenier, give me a sport. Football. Football? No. Okay. It might look like this. Here are the wage expenditures of the different teams. Here is the league position. And here is the thing. Oh, but you know what? This is from Europe, so they're actually talking about soccer. But, oh, well. At least this is the idea when you say, this is how much they're spending on their wages, and this is how well they're doing as a team. Notice it's a scatter diagram because They're not all connected. You don't draw lines between them or anything like that. It's just a collection of dots. And it looks like kind of a cloudy thing. So it's like, well, it certainly looks like you could draw a straight line in between these things, but it's very important for you to understand in statistics, the straight line does not tell you what is happening. The straight line is telling you basically an average. And it's not even telling you the real average. It's based on a sample. Okay, because the general tendency when people see a scatter diagram is they say, I want to draw a straight line so I can know what's happening. That's wrong. What's happening are the dots. What is happening is not the line. The dots are the thing that's happening. Okay? So you need to understand that reality doesn't follow a straight line. It just doesn't. Here, see from these different things. And it's in the textbook, it's on page 541. And it's the different types of relationships that you might see. You can have this kind of relationship. Let's see if we can make this bigger. Okay. And this would be a positive linear relationship. You need to understand what that actually means. A positive linear relationship means that they are both related in such a way that if one number increases, the other number also increases. So they would increase together or they would decrease together. You spend more money on the soccer team, you get better players, you win. You don't spend as much money, you don't get the good players, you lose. So then that would be this positive linear relationship. As one increases, so does the other. As one decreases, so does the other. They're joined together. But you can also have a negative linear relationship. Sometimes it's hard for people to think about something might have a negative relationship, but for example, your time spent exercising and your number of sick days. Okay, the more you exercise, the fewer sick days you have, maybe. So then you would say, okay, that's a negative relationship. More exercise, fewer sick days. If your level of exercise goes down, the level of sick days would go up. So that would be an example of a negative relationship. And again, these things are not straight lines, they're just clouds. It's like if you're on a picnic and you're lying on your back and you're watching the clouds and you say, that one looks like a bunny. That one looks like a giraffe playing the guitar. This one looks like Mel Gibson playing chess or something, whatever. All right, so then you're looking at the clouds and you're interpreting them. You're saying, what do they look like? Do they look like a positive or maybe a negative relationship? And when we talk about humility, one thing about this is you should not try to interpret a data set until you have the actual graph. You should not just say, I have numbers. You should have an actual graph to look at, because you could have something that looked like this. It's a curved relationship. One example of this is income compared to age. Most people, when they're young, don't make a lot of money. Most people, when they get really old, they also don't make a lot of money. So when you say there's a place in your life where you are making money, and then as you get older, you're just not, whether you're retired or something else. So then this would be a situation where there is not a straight line to explain the thing. It's something more complicated. Now, as it turns out, we're not going to be able to spend time to talk about that situation very much. But then this one is really common, and that is there's no relationship. Is there a relationship between your water intake and the amount of money you spend on video games? I don't know. Is there a relationship between the number of shoes that you own and the number of friends you have on social media? I don't know. But there's all kinds of things out there that just really don't connect to each other. And so then it just looks like a cloud. And if it's a cloud, then we say, oh, well, there's just no relationship between those things. So this is important for us to keep track of, to be able to say, I want to see if there's something that's happening here. Okay? Now, if we know these positive or negative relationships, this is where a lot of science comes in and a lot of other stuff. If you say something like, hey, if we increase the amount of money that people spend on computers, maybe that'll decrease the amount of money they spend on recreation. And so it's like, okay, let's figure out how much money are people spending on these things, and how does that affect the economy of a certain place or whatever. We could say something like, if we affect the amount of time children spend in, let's say, time with their friends in outdoor recreation, will that affect their discipline problems? Well then, how would we know? We would measure it like something like this. And so then we would say, number of discipline problems, number of hours spent in outdoor recreation with their friends. And so then we say, okay, maybe we should increase this, or maybe not. Okay, how do we know those things? That's what these graphs are going to be telling us. Now, it's also important for us, though, we'll talk more about some of the problems that this has as we go. So then, there are two main concepts involved in this entire process. The first thing that we want to talk about is what is called correlation. Correlation is trying to answer the question, is there a linear relationship? And what we do for this is a measurement, which I'll show you on page 544. Okay. Well, where's that formula? Do they show us the formula? Nope. Next section, correlation. Okay, so here's hours of study and the grade. Okay, so then you have your relationship here. You draw this. Here is how many cars are in a company and how much money they make. Okay, a rental car company, it has thousands of cars. Does that necessarily mean that they're making more money? Well, it looks that way, right? So it certainly looks like if a company has more cars, they're making more money. Seems reasonable. How about if somebody's absent from class, does that make their grade go down? Yes, it does, supposedly. But where do they have that? Oh, here it is. Here is the formula for something that we're not going to do. Okay? I want you to see the formula and then say, wow, I am so glad we're not going to do that. Right? So this letter R is called the correlation coefficient. It's also called the PPMC, but that's not very common. And in fact, most of the time, it's just called the correlation. And notice all of these X and Y values. Your data set, you take all the X's and add them together, you take all the Y's and add them together, and then you also multiply them and you do all this stuff. And it's really complicated. So we don't want to do that. What we want to do, then, if I can make this happen. Okay, I'm going to go to what your homework assignment is going to look like. Okay. In your homework assignment, you're going to get something that looks kind of like this. It's going to have the price of oil and also the price of gasoline. Now, it seemed to make sense that the oil and the gasoline would be related, right? So I'm going to click this and I'm going to download my data. Okay? And it's going to get into a Microsoft Excel file, which I'm going to click on. And it says I need to enable editing, which I will do. Okay? So I'm going to make this font size larger so you can see it a little better. Okay? Here's the oil and the gasoline. Does it look like if you have a higher oil price, you'd have a higher gasoline price? Kind of looks that way. Okay? So what we're going to say, though, is there a way to measure how strong that relationship is? So I'm going to hit an equal sign, and I'm going to type this right here, C-O-R-R-E-L. Okay. Then I'm going to put a left parenthesis. Then I'm going to select one column here. Doesn't matter which one I do, but I'm just going to do the first one. And these are the numbers of the oil prices. Then I put a comma, and I select the gasoline prices. Then I hit right parenthesis. And again, you see the word or the formula, equal sign, C-O-R-R-E-L, parenthesis. First column of data, comma, second column of data, parenthesis, equals that number right there. Now, what we need to then understand, what does that number mean? Using this formula to give us our correlation coefficient, what does that actually mean? And the meaning of that is given to us on page 544 in the textbook. Right here. If I had an R value of 0.50, and it looks kind of cloudy, but it's kind of going up. If I had an R value of 0.90, it's more tight around that straight line. And if I had an R value of +1, they would be exactly lined up on the straight line. So the correlation coefficient is a way to measure the strength of a linear relationship. When we say linear, we mean it's on a straight line. Well, what happens if we have some kind of negative relationship? We would use the same formula, but the number that we come up with would be a negative number. So an R of negative 50 is going down. R of negative 90.90 is also going down, but it's tighter to the line. R of negative 1, it's an exact straight line like this. So what I'm going to show you is a scale that demonstrates that measure. 0 is in the middle. That would be no linear relationship. Over here, we could have +1, which would be a strong positive, and -1 would be a strong negative. So if we look at a cloud of data values and we can say, well, it looks kind of strong, but I'm not sure exactly how strong, this would be a way to actually measure that. If R is close to a +1, it's a strong positive. If it's close to -1, it's a strong negative. If it's somewhere in between, well, it's something, but it's not necessarily strong. So then, when we say, how do I actually use hypothesis testing to make this work? I'm going to set up a hypothesis test. For correlation. So right now I want you to have that sheet where it goes through the steps for hypothesis testing so that you can understand how this is going to work. It's kind of different though, based on what we're going to do. Okay? So how does hypothesis test work for correlation? What's the first thing that we need? Abby, can you tell me what's the first thing I need for hypothesis testing?
State the hypothesis.
Okay, so we need to state the null and alternative hypothesis. Well, in order to do that, we have to have the symbols that we're going to use. So when we talk about correlation, the sample value is R. R comes from the data, just like the sample mean or sample proportion or anything else. It comes from the sample data. But what is the population symbol? Well, I have to apologize ahead of time for this symbol. Okay? It looks like this. All right? It's not a P. It's called rho, R-H-O, Greek letter. It looks like a P, but it's not a P. It's called rho.
Sideways like that always?
Sure, yeah. It's always kind of curved, and it kind of has this little thing with the kind of narrowness of the, whatever. So yeah, it's not a P. It looks like one, but it's not one. Okay? So if I go to page 547 in the textbook, you can see it. Test the hypothesis, the null hypothesis that rho is equal to 0. Okay? So this is what we have. The null hypothesis is that rho is equal to 0. That would be no linear relationship. Well, what's the alternative hypothesis? Well, it's two-tailed. It's rho not equal to 0. Because we're talking about being strong either way. It could be strong negative or strong. Does that actually work? Well, what's the second thing after determine hypotheses? Donna, can you tell me the second thing?
Find the critical value from the appropriate table.
Okay, so I need to find a critical value. And these critical values are in the textbook. And we'll see if we can make it happen here. Now, no. Okay. Critical values for the PPMC. Does it say it's on 658? I think it does. Okay. Page 658, critical values for the PPMC. And it's table I. Okay, we had E, F, G, skip H, I.
Well, we not use our old tables anymore.
No, we will use them, but not for this section. Okay. Right here, as you see, there are degrees of freedom. And I have to apologize again for this. Degrees of freedom is n minus 2, not n minus 1. And note on the table, we have two possibilities, alpha 0.05 or alpha is 0.01. Most of the time, we use 0.05. Okay? So, 6. We had 6 different times that we did measurement. Every time we measured, we got 2 things, but the actual number of samples or the number of times we did it would be 6. So there are 6 objects being measured. So degrees of freedom here would be 4. Okay, you count the number of rows and then subtract 2, degrees of freedom would be 4. Okay, so if I go back here and I say degrees of freedom is 4 and I'm going to use alpha 0.05, that number right there, you might not be able to see it, but it's 0.811. So here I have my critical value of 0.811. The way that this works, because it's two-tailed, okay, this is two-tailed. Here's -1, 0, +1. We take 0.811 and we make a negative and a positive. That 0.811 has to be put in as a positive number and also as a negative number. And then when we say rejection region would also be two-tailed. It goes both directions. Once again, we didn't have this before. We're having it now. Previously, the only thing that was two-tailed was confidence intervals. But now this is a hypothesis test. It's two-tailed. And so we have a positive. We also have a negative. The rejection region is shading the tail parts on the outside. Okay, so this is critical value and rejection region. Okay, so Taylor, what's next in my list of things?
You need to compute the test value.
Okay, the test value is R, which we got from the computer. So if I go back here, R is the test value. In the example that we're doing from the computer here, it comes out to be 0.853. So we don't have to go through that long formula. We can just use the value of R, the correlation. That's what's being talked about here. And so what we're saying here, is this R strong enough to be significant? Is this just a fluctuation somehow, or is this a real strong relationship? And that's what the hypothesis test is going to prove, that it is significantly strong. Okay? So, Allie, I think it's your turn. What happens next? Okay, so what happens here, Allie? How do you know? This number, 0.853, is that in the shaded region?
Oh, wait, 8.5, yeah, sorry.
Yes, it is. So yes, it is in the rejection region, so therefore we do reject the null hypothesis. Okay? Test value is in the rejection region. So we do reject the null hypothesis. Brianna, I don't know if I skipped you. Did I skip you?
Yeah.
All right. So what do we do if we reject the null hypothesis? What does that mean? There is enough evidence for what?
Something about the null hypothesis, don't know what though.
The alternative.
That.
Okay. There is enough evidence to prove the alternative. Well, the null hypothesis was no relationship. So the alternative hypothesis, there is relationship. So what this is telling me, and again, it's a positive number, so then I would be able to say, is it true that the higher the oil prices, the higher the gasoline prices? Yes, it's true. It's not exactly true because it's not a 1, but it's true enough. So we say yes, there is that relationship. All right, so the trouble that we have with this is that we don't necessarily know the direction of the relationship. Is it true that when the oil price goes up, that makes the gasoline price go up? Well, probably, because oil comes before gasoline, right? You know anything about it. But let's say this. Is it true that people who get more exercise, that because they exercise, they will have, because they'll exercise, they'll have more vitamin D in their system? Let's just say that's a thing. Well, it might be. Or is it possible that people who have more vitamin D in their system will feel better and they're better able to exercise because their joints don't hurt as bad or something like that? We don't know. And here's one that might trip you up occasionally. Is it true that people who are successful academically are better employees? Well, maybe. But it's also possible that people who would be better employees would also be successful academically. So maybe it's not the academics that makes the person a hard worker, but a hard worker will do better at academics. So it's not necessarily true that one thing actually causes something, even though they might be connected. For example, is it true that if people spend more money on x-rays, that they'll also spend more money on their pets? As it turns out, it is. Does that mean if you get an x-ray, you're more likely to have a pet? No. What it means is people who have more money like to spend it. And so if you have a lot of money, when somebody says, hey, you need an x-ray, sure. Maybe half a dozen of them. Are they cheaper today or something? And if they have a pet, oh, I love that little sweater. I'll get it for the pet. Okay? But if you don't have a lot of money, maybe they'll say, oh, you should maybe get an x-ray. Maybe I won't. And maybe I'll just have my pet dress in their own clothing instead of buying extra stuff. So then it's like, you don't necessarily know that if one thing changes, it makes something else change. Does the clock over at the church over there, does that make this clock go up to 4 o'clock? No. Does this clock going up to 4 o'clock, does that make the chimes ring over in that church? No. But they both go at the same time. So just because two things happen, and they happen more often, does not mean that one of them necessarily causes the other one. All right, so yeah, we need to take a break. We'll come back at 4:10. Talk about the other thing, and then we'll have a few minutes at the end to use the computer.